morning, friends and dear students. I am here for my course, that is Flight Mechanics. This course belongs to the fourth semester of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have started my Module 1. In Module 1, we have initially discussed about atmosphere, then left, drag polar, then different types of air speeds, that is equivalent airspeed, true airspeed, calibrated airspeed. Then we have also done for the thrust required, power required, thrust available, power available, and also we have seen different phases of the flight. So if this is the aircraft, so phases of the flight means aircraft will, from the taxi it will start, it is a taxi. From the taxi it will go to the runway and it is called the takeoff. In this takeoff, aircraft has to fly with a certain speed, and that speed where you will get sufficient amount of lift which can be able to counter the weight of the aircraft. From there onwards it is called the takeoff, and from there it is climb. Climbing means it will have some angle and it will go up like this. So it is called the climb. So first is the takeoff, then climb, and after reaching a certain height, aircraft will go in the same altitude. There will not be any change of altitude. That is called the cruise. And most of the distance which is covered by the aircraft is a cruise flight. In the cruise flight, we have seen that equation of motion, that lift is equal to weight and the thrust is equal to drag. This is the basic equation of motion for flight mechanics. But it will give lot of ideas, lot of concept. In this, our aircraft should not go less than the stall speed. After reaching to the cruise, when you are reached before your destination, some 50 miles away from the destination, aircraft will descend. So it is going down, descent. When you reach to certain height, and if the aircraft is not cleared for the landing due to some obstruction or some already aircrafts are there on the queue, so aircraft ATC will tell the pilot to loiter, and the loiter means around the certain area aircraft will be circling in a given height, given altitude. That is called the loitering. As and when the runway is clear, there is no disturbance in the airspace of that ATC. ATC controller will give the direction that you are clear to land, and aircraft will position for the landing, and that is called the approach. So as you reach approach and you are touching down the runway, then it is called the landing. So these are the few phases of the aircraft which we have already discussed. In our previous module, we have also discussed about cruise, then climb, then maneuvering flight. In that we have the accelerated flight of turn and also accelerated flight of maneuver, vertical maneuver, that is pull up and the pull down. Then something we have discussed about landing performance, fuel reserve, safety of the aircraft. Most of the things we have covered. Now onwards we will be discussing about the numericals or problem solving, and today we are here to problem solving related to takeoff and landing performance of the aircraft. I am Dr. Yagya Dutta Dwivedi, professor from Institute of Aeronautical Engineering, Department of Aeronautical Engineering, Hyderabad, India. Today's topic we are going to discuss about a few numericals about landing and the takeoff, and the first numerical is here. That so in this, the aircraft, the trainer aircraft, that is name is Embraer EMB 312 Tucano has a turboprop engine with a variable pitch propeller and a takeoff mass of 2550 kilograms. The aircraft cruise speed at 10,000 feet is 172 knots true airspeed, that is KTAS. Other aircraft features are as follows. S is equal to 19.4 meter square. Power maximum is 750 horsepower. Stall speed is 67 knot. CD naught is equal to 0.021. CD takeoff is equal to 0.004. CD naught of landing is 0.007. B is equal to, span is equal to 11.15 meter. E is equal to 0.86. Delta CL FRO is equal to 0.4. Calculate the takeoff run, that is STO, that is distance of takeoff for this aircraft at sea level. If it is taking off from a dry asphalt runway, air density at 10,000 feet is 0.90 kg per meter cube, and the runway friction coefficient mu is equal to 0.04. So this is the problem. We have to find out the takeoff distance S takeoff. So this we will see here and we will solve this problem. So we will start with here that what are the parameters given. So first is the mass. M is equal to 2550 kilogram. We can write it as a 2550 into 9.81 Newton. This is the mass. Speed of this thing is given in V is equal to 172 kts. This is the true air speed. Power maximum P max is equal to 750 horsepower. Stall speed is 67 knot. Delta CL FRO is equal to 0.4. CD naught C is equal to 0.021. CD naught for takeoff is equal to 0.004. CD naught for landing is equal to 0.007. Span B is equal to 11.14 meter. E is equal to 0.86. Delta. Okay, so here rho at 1000 feet is given as 0.904 and the friction mu is equal to 0.04. So these are the parameters which are given for the aircraft. So we will see first we have found the ground roll, that is the ground roll distance, ground roll, and we know that CLC is equal to 2W by rho S VC square, and W is equal to mg. So 2 into m into g divided by rho S VC square. 2 into m is equal to 2550 into 9.81. Rho is here, it is given 0.904 in this. Rho is given. S is here area. Area S is given 19.4 meter square. So 19.4 into VC. VC is 172 knots. So 172 into 0.5144 to convert knots into meter per second. So here we will get this CL, C is equal to, we will get 0.364. So one parameter, that is the coefficient of lift, for this condition we have got 0.364. Now we have to find out the CL for the takeoff. And this CL of the takeoff is equal to C plus delta CL FRO. This delta CLC we have just find out here. FRO is here, it is already mentioned here, 0.4. So 0.364 plus 0.4. So here we got it at is equal to this, we got, if we add it, we will get 0.764. This we got the CL of takeoff. Now we have to find out the CD naught of the takeoff. And this CD naught is equal to CD naught of the C plus CD naught of from. So this you can find out that CD naught is equal to 0.021 plus 0.004. Okay, plus here CD naught of LG. So CD naught of LG 0.007. So you will get 0.032. So this you got total CD naught for the takeoff condition. Before we start further, we have to find out the aspect ratio. So this aspect ratio, we know that it is B square by S, where S is the area, B is the span. B is here given 11.14. So 11.14 whole square divided by 19.4. So you will get this as a 6.4. Now we have to find out the factor K, which is 1 by pi aspect ratio into E. So 1 by 3.14 into aspect ratio we have got 6.4. 6.4 into S, E is equal to 0.86. 0.86. So this value of the K you will get as 0.058. So we got the K, we got the aspect ratio. Now we will see that CD naught takeoff, we have to obtain total CD for the takeoff. So CD of the takeoff is equal to CD naught of takeoff plus K CL square of takeoff. So CD naught we have just now here 0.032, 0.032 plus K we got 0.058 into CL. CL we have got here 0.764 here. So 0.764 square. If we solve this, we will get this CD naught is equal to, so CD naught takeoff is equal to, we will get 0.066. So we got now CD naught, this is the total CD, it is not CD naught, it is a CD takeoff, 0.066. Now we have to find out the maximum lift coefficient. So CL max is equal to 2W divided by rho S Vs square. Vs is a stall speed, and so 2 into M 2550 9.81 divided by 1.225 into S is 19.4. Here is V square is Vs is a 67 into 0.5144. To convert in knots to meter, we have to So we will get this value as 1.77. So we got the CL maximum also. Now we will see that how we can go ahead, and we know that the rolling distance SG equation is M divided by rho into S CD of takeoff minus mu CL of takeoff log natural. We will have T by mg minus mu divided by T by mg, that is weight, minus mu minus KL square CDLO minus mu CL takeoff divided by CL max. So this is the equation to find out the ground roll, and all the parameters we have already find out. So now we will put the value. Mass is equal to 2550 divided by 1.225 into area is 19.4. CD naught we have find out, this CD naught minus is 0.035 ln 0.354 minus 0.04 divided by 0.354 minus 0.04 minus here KCL square, it is 1.1 square into 0.35 divided by CL is 1.77. This is here. If we simplify this, we will get SG is equal to 242.9 meter. So this is the ground roll distance. This we have find out. Now we have to find out the, it is A part is done. Now we will go for the part B. I will change the color for the part B. It is now blue. So we have to find out the rotation or translational run on the runway. So if I make here, this is the runway. So here is your aircraft. This is your aircraft. This is up to here to here. From here it is rotational. This is the rotational or translation. This distance. This is the SR, and from here to here it is the SA, and from here to here it is a SG. Okay, so this we can SR, it is called SR. This SR is equal to TR into VR. TR into VR. So we can write down that here TR is equal to 1 into 1.1 into 67 is velocity and 0.5144. You will get here 37.9 meter. So this rotational velocity is 37.9 meter. And this is the SAR. SA is a accelerated flight. So now we have to see the next, that C part. This I will change with red color. So this C part I will violet color. So this C is airborne section. So if you see here, this is the aircraft. If your aircraft is here, this is the aircraft. It will accelerate from 0 to this. This is the accelerated distance, and from here wheel will be touching, but it will go like this. This is the rotational, and from here, as and when it is clearing the 50 feet, this is your airborne section. So we have to find out that SA. This is the SA. So this SA is equal to mg divided by TAB minus DAB, V2 square minus V liftoff square divided by 2g minus HO. HO is this distance. So now we have to find out now TAB. So it is a TAB is equal to NAB into P max, this is the efficiency, divided by KAB VS. So we can now write this thing as NAB is 0.8, 750 into HP to watt, 746 divided by 1.25 into 67 into 0.5144. So you will get this as a 10,385 Newton. So we got this TAB. So here we have to again find out the CL at airborne. This is the CL max by KAB square. CL max is 1.77, we have find out, and we have got the value of K is 1.25 square. We will get this as a 1.134. Now we have to find out the CD. Total CD at airborne is equal to CD naught at takeoff plus KCL square A. So this you will get 0.032 plus K is equal to 0.058 into CL square, K into CL square. So 1.134 square. So this you will get 0.106. This is the drag. So now we have to find the total drag. DAB we got. Now DAB is equal to half rho V rho S CDA into V square. So here 1.25 into V2 square. So half into 1.225 into 19.4 into 0.106 into 1.25 into 67 into 0.5144 square. So this DAB we will get here 2346 Newton. So in this equation we have now got this, we have got now this. So now we have to find out SA. So here SA, if I put this all value SA, we will get here that 2550 into 9.81 here mg divided by TA. TA I have got 10385, then minus 2346. Now I have to make V square. So V square is 1.3 into 67 into 0.5144 square minus 1.2 into 67 into 0.5144 square divided by 2 into 9.81. So I got here SA is equal to 94.5 meter. So I got this also. Now we have to find out that if the obstacle is 50, where the obstacle is given, obstacle for clearance is 50 feet, that is 15.24 meter. So SA is equal to under root SA square minus HO square. So SA, I have got 19.5 whole square minus 15.24 whole square. I will get SA is equal to 93.3 meter. So this is the airborne distance. Now the last and the final requirement is D, that is the total takeoff run. Total takeoff run, that is STO. So STO is equal to SG, ground roll, plus rotational, plus airborne. So here you will get 242.9 plus SR, we have got 37.9 plus 93.3. Okay, here. So total we got here that STO is equal to 374.1 meters. So this is the answer for the problem. So in this way we have solved this problem and hope this will be useful. Now I will discuss the numerical number 2. So this I am going to read out. Using the average acceleration method, find the maximum power takeoff ground roll. SG, we have to find out for maximum power with no wind and a zero runway slope. There is no wind, wind is zero and the runway is not very straight, horizontal, for a 12,000 pound T-38 at sea level and 6,000 feet given the following conditions. So here we have two conditions, at the sea level and another is 6,000 feet. So in this only density will vary, rho is vary. This we know that at the sea level the density of the air is 1.225 kg per meter cube. As you go up and up, this density will reduce. So your parameters where rho is coming, you put this for the sea level and for the 6,000 feet we can find out from the table. Here the area is 170 feet square. Please excuse me, here I am using the another units, that is the FPS unit, and CL maximum is 0.88, mu r, that is the frictional coefficient, is 0.025, CD naught is equal to 0.02 and K is equal to 0.2. So now we have to start this problem. Here given in this problem the mass or weight of this thing is given. Weight is equal to 12,000 pound. Area S is equal to 170 feet square. CL max is given 0.88. Mu r is given 0.025. CD naught is 0.02. K is equal to 0.2. So we will start first with sea level. Sea level, here rho is equal to 1.225 kg per meter cube, okay, or 0.00238 slugs per feet cube. Okay, so first we have to find out the stall speed. Stall speed Vs is equal to under root, we know that 2W by rho SCL max. So here W is given, so 2 into 12,000 divided by 0.00238 rho. S is equal to 170 feet square and this is the 0.88. So you will get 259.6 feet per second. So we got this Vs. And we know that there is some relation between Vs and the V liftoff. It is 1.1, 10% extra. So V lift off is equal to 1.1 Vs. So 1.1 into 259.6. So you will get this as a 285.6 feet per second. So we got this V lift off, and we also know that for the average, we have to take average of the velocity. So average velocity is equal to 0.707 into V lift off. So 0.707 into 285.6. So you will get 201.9 feet per second. So we got the V average also. Now if you want what is the Mach number? So average Mach number M is equal to V average divided by SA, sea level, and we know that the sea level speed of the sound is 1116.4. So we will get 0.181. This is the Mach number of this aircraft. This is the M. So it is given that T average is given as a 6,000 pound. So we can find out the CL of liftoff is equal to mu r divided by 2k. Mu r is 0.025. 2 into k is 0.2. We will get 0.6. And CD average is equal to CD naught plus K CL liftoff square. CD naught is 0.02 plus K is 0.2. CL is equal to 0.06 square. So you will get here this as a 0.0208. So this is the average drag. We got average drag now 0.0208. Now we have to see the average dynamic pressure, because we are taking everything average, so we have to take the average dynamic pressure, that is Q bar average is equal to half rho V square average, half into 0.00238 into V is equal to 201.9 whole square. So this you will get here 48.5 psi. This is the Q average. Now we have to find out the average acceleration. Average acceleration A bar is equal to G by W into T average minus D average minus mu R W minus L average. This is the equation, and here we have all the value we have. So G is equal to 32.2, W is equal to 20,000, T average is equal to 6,000 minus D average is equal to D average. We have seen that it is 0.0206 into area 48.5 into 170 minus 0.025, that is a mu r, into W is 12,000 minus 0.0675 into 48.5 into 170. So here you will get this A average is equal to 14.9 feet per second square. So now we got this average acceleration. So we can find out the ground roll distance. So SL is equal to 1 by A bar square V square G divided by 2. So we can write it V square G by 2 A bar. V, it is given 285.6 whole square divided by 2 into 14.9. This you will get 2737 feet. So this is your SG at sea level. Okay, so for the sea level we have done it. For sea level we have done. Now same way you can do for 6,000 feet altitude. Find the air density from the ISA table. You will get this value SG at 6,000 feet. 6,000, you will get answer 3909 feet. Same way, only for rho you have to put this value and you will get all the required things. Now I will go for the third problem, and in this problem you will see that I will just read out this problem, and using the average acceleration method, find the maximum power takeoff ground run with no wind and a zero runway for a 6,000 kg T-38 sea level and 6,000 feet given the following condition. Okay, so here it is like a same problem as earlier we have done. So we will see what are the things given. So using average acceleration method, we will use average acceleration method. Using average acceleration method, maximum power takeoff given. In this problem, what are the parameters are given? First is the mass, 600 kgs at 6,000 feet. Area S, 15.8 meter square. CL max, 0.88. Mu r, 0.025. CD naught 0.02, K is equal to 0.2, T average is equal to 6,000 kg. So these are the parameters which are given. So we should see we have to find out the sea level. I will just change the color of this my problem. So now at sea level, rho is 1.225 kg per meter cube. We have to find out the stall speed. Stall speed of aircraft, that is a Vs. So we know that this Vs is equal to under root 2W divided by rho S CL max. And if we see some relations, Vs and the V lift off, so I will just, so V lift off is equal to 1.1 Vs, V average 0.707 V lift off, and Mach average is equal to V average divided by A. So these are the some problems which are we should understand and we should know. So we have to find out first CL for the CL opt, that is mu r divided by 2k. Mu r is 0.025, k is 0.2. You will get 0.0625. So this you got CL opt. Because we have to find out this, because we want to find out the CD average. So this is equal to CD naught plus KCL opt square. CD naught is 0.02 plus K is equal to 0.2. CL opt we got 0.0625 square. So this we will get drag average is equal to 0.0208. This is the CD average. So now we have to find out the Q average. Dynamic pressure average is equal to half rho V square, average V square. So we can find out by the putting the values here. But we know that the acceleration, average acceleration, that is called average acceleration, A bar is equal to G by W T average minus D average minus mu r W minus L average. This is the equation for the average acceleration to find out the ground roll. And we can see that SG at sea level is equal to 1 by A bar Vg square by 2. So now by using this we can find out, okay, all the parameters whatever required, and we can solve this problem. So we know the W, we know the T average, as we have seen in the previous questions. We can find out this all things. So if you you can get this D average also, because we got this CD. So this D is equal to half rho V square S CD average. You know the V all the things are known. This you can get the D average. So in this equation, if you see D average, T average is given, mu r is given, W is given, L average also we can find out, and putting this value we will get SG. So in this way we can solve these equations. So we will see the next equation, the next problem, that is a T37 has a drag polar. CD is equal to 0.02 plus 0.057 CL square. Find its maximum glide ratio and maximum glide range from 2000 feet to sea level. So at two conditions here, if you see by this equation, we can find out that this is the K and this is the CD naught. So in this way we can find out this. So the maximum glide ratio occurs when L by D is the maximum, where CD naught is equal to KCL square. Thus R by H maximum, that is L by D maximum, is equal to CL by CD maximum. And we know the CL is equal to under root CD naught by K by 2 under root CD naught. So if you simplify this, so here is the 2 and this is the under root CD naught. Here, if you want in the bracket, it will become the, okay, just if I want everything in bracket in this root. So here it is a CD naught by K divided by, I will take here 2 and here I will make CD naught square. So this CD naught and this is square is cancelled. So here you will get 1 by 2 under root K CD naught. And we know all this K is equal to 0.057 and the CD naught is 0.04. We will get this maximum 14.8. The maximum glide range from 20,000 feet would be, so if you want R by H is equal to 14.8. So maximum range R is equal to 20 into 14.8. You will get 56.1 mile. So L by D is equal to also range by height, altitude. So in this way we can find out. So next lecture we will be solving the problem from straight and the level flight. And the references are Anderson Jr. Aircraft Performance and Design, International Edition, McGraw-Hill's first edition 1999. SL by ME Aircraft Performance Theory and Practice, AIA Education Series, AIA. Any questions, you are welcome to ask. My email is ydwedi@gmail.com. Please do like and subscribe my channel. If anywhere you feel it is not clear, you can also write in the comment box. I will be trying to reply your answer, your questions. Please be tuned for my next lecture, and next few lectures are only the numericals. I will be solving the numericals for different units. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.